Good evening. We have 2 more talks today. Very interesting day, a lot of very interesting subjects and topics, very diverse. So, the next speaker will be Professor Marty Gregg from Belfast. Hi, Marty.
How's
Do
it
you
going?
hear us?
Yes, very well, thank you.
Yeah, we hear you also. Marty will talk about conducting piezo something. I don't know. I don't have my glasses, sorry. So you can put the title on the screen. Please proceed.
He's going to talk about something, and that's fine. So I'm very jealous that you guys are getting a face-to-face meeting, and I'm probably more jealous that you're getting face-to-face dinner and a few beers. I'm now wishing that I was there very much. I hope you're all well. Okay, so I'm going to talk about conducting ferroelectric domain walls. If I can sort of use this. Great, no, it's not responding. Okay, so look, we've been looking at this sort of area of research for a large number of years now, and in fact, well, there are many people who have contributed to the work, so that was the slide that you almost saw there. I think one thing that is slightly embarrassing to note about conducting ferroelectric domain walls is that this is now an established scientific area. Mature is maybe too strong, but it's 12 years since these nice images were first published by Jan Seidel and co-workers. And since then, there have been, there's been a sort of discovery phase where we have found out that it's not just domain walls in bismuth ferrite that can conduct, but also, in PZT, in barium titanate, in lithium niobate, in a range of proper ferroelectrics, and also in a range of improper ferroelectrics. And in some senses, improper ferroelectrics are even more robust because quite often the conduction that's seen at these domain walls that you can see picked up here in conducting atomic force microscopy is related to some kind of discontinuity in the polarization across the domain wall. And that often is easier to maintain in an improper ferroelectric than in a proper ferroelectric. So, in some senses, there was a phase of discovery of conducting walls in ferroelectrics, then there was a phase in proper ferroelectrics, and then there was a phase of discovery of walls in improper ferroelectrics. And here's another couple of examples. Probably the most work that has been done in this field is on the manganites and in the boresites. Okay, now we do have an idea as to why domain walls in ferroelectrics might conduct. In fact, several ideas. And there is indeed evidence in the literature for all 3 of these kinds of notions for what makes a conductive wall conduct. The first one is that basically they're not really conducting, it's just that they're kind of hoovers for the aggregation of defects, charge defects, that can act as defect donor or dopant sites within the band gap of the normal material. And I think, Igor Stolichnow's seen some really nice evidence that in bismuth ferrite, this collection of defects certainly occurs. There's also evidence in bismuth ferrite that in some instances, the band gap is reduced as a result of the existence of a domain wall. So, you reduce the band gap and then you increase the number of thermally induced carriers. One study that I've seen has explicitly seen this suppression of the absolute energy of the conduction band. And then the sort of third and most popular piece of physics behind the conduction of domain walls is for when there is a polar discontinuity, as I say. So here, if you've got a head-to-head polar discontinuity, then you end up with bound charge locally that's positive. That's going to increase the stability of negative charge carriers. And so you see effectively band bending to lower the energy associated with electrons should they go there. And similarly, if you look at a tail-to-tail, you destabilize the existence of electrons at that point, but you can, through warping the energy space, you can leave out the possibility of intrinsic holes developing to facilitate conduction. Okay, so these are three ideas, but it has to be said that for a field that is 12 years old, the direct evidence and the quality of the direct evidence, there's plenty of circumstantial evidence, don't get me wrong, but direct evidence that actually goes towards telling us what the physics of transport really are is a little bit slim. And certainly when you look at all of the plethora of characterizations, transport characterizations and so on that Pep and Valerie were showing there in strontium vanadate, taking it for granted that this is what you do. Similar experiments, similar insights have not really been developed for conducting domain walls. Let me give you an example. I'm sounding like a preacher now, but let me give you an example. As far as I'm aware, there are no 4-probe measurements of resistance in conducting ferroelectric domain walls. There are plenty of 2-probe, but as far as I'm aware, there are no 4-probe. And so an awful lot of the conductivity information that you extract from literature is probably more to do with the physics of the barriers at the electrode junction between the electrode and the domain wall than they are about the intrinsic properties of the domain wall themselves. So I'm saying that there's an awful lot of catch-up that we need to do as a community here in order to better understand the physics of conduction and the physics associated with the generation of the conduction in these walls. Okay, look, we've been trying, okay? There's a number of people at Queen's and the collaborating groups that have been trying. But as you'll see, the amount of success that we've had in terms of revealing fundamental aspects of conduction and carrier behavior, pretty limited, given that we've been at this for about 6 years. Okay, but I'm going to describe to you very briefly some things that we've done that are now well established, these nanoscale Hall effect measurements. And I'm also then going to spend a little bit more time talking about these more recent geometric magnetoresistant measurements that we've been doing that we still haven't yet published. Okay, so nanoscale Hall effect. Most of the work here we've done on manganites. Manganites are interesting because they have such, aesthetically beautiful microstructure, but also you can see that the domain walls here meander rather strongly, even in a single crystal where there is only, there are only 2 directions, of polarization. It's a uniaxial system. So what that means is that, somewhere in this, mass of microstructural complexity, you're for sure going to find polar discontinuities. And in the initial work that Dennis and co-workers did, they found that the tail-to-tail polar discontinuities across walls that were tail-to-tail, that those were the ones that were giving the most conduction. And so we concentrated on tail-to-tail. It turns out that since then, Dennis has shown that you can get conduction if you drive it a little harder on head-to-heads, and you can also even get conduction on the neutral walls. Okay, so I don't want to spend a lot of time on this because this is old work now, 2016. But what we did here was we used the AFM really to pick up the Hall voltage. So we drove a current from source to drain along one of these conductive domain walls in the presence of a magnetic field. And the geometry was roughly that, such that we could pick up the Hall voltage that we expected to be generated on the top surface here through the AFM tip. Initially, that was done in a fairly experimentally poor manner, I guess, in the sense that we were trying to pick up a voltage, but actually the voltage came through in the topography signal. So here you can see topographic images where there are plenty of domain walls and where we're driving current, sometimes in the presence of a magnetic field. And you can see that you don't see any contrast apart from this big scratch until you drive current and have the magnetic field on at the same time. And then the additional sort of topography you get is associated with the current carrying domain walls. So we interpreted this as a manifestation of the Hall voltage, and we kind of calibrated it and we worked out various aspects of behavior in terms of carrier type, yes, but also carrier mobility and so on. But the bottom line was that we weren't very satisfied with those measurements because they weren't a direct measurement of the Hall voltage. And so to get a direct measurement, we did basically the same experiment, but this time we used the AFM to pick up the Hall voltage through Kelvin probe force microscopy. And here's an example of the interelectrode gap region in those types of experiments. And what you see here is the contrast from Kelvin probe force microscopy. So on the right-hand side here, the bright colors indicate a high potential. On the left-hand side here, you can see the darker colors indicate a lower potential. So you have a potential drop across the interelectrode gap. And you can see some sort of evidence here of these kinds of meandering domain wall features, conducting domain wall features that you see in the manganites. But they're not really popping out very strongly, and certainly this is no advert for using KPFM for measuring the Hall voltage. However, what you can do, a really nice experimental trick, is that you can do this potential mapping with the B field in one direction, and then keeping exactly the same geometry, the same driving voltage and so on. You reverse the sense of the B field, and that then means that everything except for the Hall voltage stays the same. You can take one image away from the other, and you end up with an image of the Hall potential, a spatial map of the Hall potential, or twice the Hall potential or something. So here's what happens when you do that kind of image subtraction. And you can see now that the domain walls that are conducting are really shining through in the image. And if you look at this section of the Hall voltage, you can see that there's a little bit of a dip here, but basically this is noise. And then, let's go back there. And then, at this point here, this correlates to this dip in Hall potential. And interesting, this correlates with this peak in Hall potential. And the fact that you can get dips and peaks in the Hall potential driving the current in the same direction under a magnetic field, which is notionally the same, indicates that there are two kind of carriers active here. And that's what we expect. So in the tail-to-tail walls, we expect holes. In the head-to-head walls, we expect electrons. Good. Okay, in terms of extracting information about the carriers, not just the carrier types, here we got pretty clear data suggesting that the carrier mobilities were of the order of hundreds of centimeters squared per volt second. Now, what does that mean? Well, when we first got this data, it was no surprise to me. I had no preconceived ideas of what the mobility should be. But it turns out when you compare this to literature on oxides, this is pretty much the highest room temperature Hall mobility in oxides that exists out there. And it suggests that there is something quite interesting about the carrier behavior and the transport physics in these domain walls. Okay, so that's what we got on the manganites using Hall effect measurements. Let's now go on to more recent measurements of magnetoresistance in lithium niobate. Okay, so lithium niobate is an amazing material. Conduction in domain walls first reported in 2012, so almost 10 years ago. And what I really like about lithium niobate is this breakthrough result published by Werner et al., that the conductivity of the charged domain walls is more than 13 orders of magnitude higher than that of the domains themselves, that of bulk. And this is in a 2-probe measurement. So that's 13 orders of magnitude higher, including presumably some kind of shocky barrier contact. That's remarkable. And certainly the relative ratio of the conductivity of the walls to the domains is higher in lithium niobate than in any other system. And that makes it interesting. What on earth is the physics that's going on there? And it also makes it very suitable for doing transport measurements. So that's why we started to look at it. So here are our samples. This is a cross-section of the sample. You've got an LNO film. You can get these from NanoLN, a company in China. They're just smart cut single crystal films, a couple of 100 nanometers thick, from 300 to 500, I think. The LNO sits on top of, you can order it so that it's sitting on top of a lower electrode, then a silica buffer, and then a sort of bulk LNO handle wafer is what it comes on. Now, as I say, what's really nice about this system is that when you're doing transport measurements between a top electrode and a bottom electrode, you can be 100% sure that the current that you are monitoring and the changes in current that you're monitoring are associated with the conduction along the domain walls. That is not true in the manganite system. So, you know, in manganites, here you can see from Jakob and Dennis and co-workers, that the relative ratio of the conduction in a tail-to-tail wall over the conduction seen in a bulk domain is a factor of 4 or 5, right? Here, it's 13 or 14 orders of magnitude difference. So we have used that, I think, to our advantage. Okay, now the first thing to note about this lithium niobate is the morphology of the domain walls themselves. So this is a plan view image of some domain walls just taken with PFM. And you can see that on the top surface, the locus of the domain wall is pretty much a whole series of circles. Sometimes they coalesce, yes, but in the majority of cases, you have isolated circles. The cross-sectional view, so this is cross-sectional STEM information, shows sort of isosceles triangles in terms of domain morphology. And so in 3 dimensions, these domain walls look like conical surfaces. Now, what I want to show you is that when this is the case, okay, this is just showing you that these domain walls carry a lot of current between the top surface and that lower electrode that I was showing you in the schematic. Okay, but the real money here is in the realization that to a first approximation, this conical morphology of the conducting pathway in the LNO domain walls is very similar to a Corbino disk. So the top electrode here just contacts this top rim of the domain wall at the top surface. The lower electrode contacts this lower circumferential ring at the lower electrode. And you know, the projection of that onto the XY plane is in fact the perfect Corbino disk, where you have an inner electrode, an outer electrode, and an annulus of material that you're trying to characterize. Now, the Corbino disk is a classic geometry for measurement of geometric magnetoresistance. And so we've kind of called these Corbino cones by analogy. Okay, now there are a number of reasons why we think that this conical morphology gives effectively the Corbino disk morphology. One is that when you're applying a magnetic field along the conical axis, then the plane in which the Lorentz force, or the magnetic component of the Lorentz force, is felt is the XY plane. 2 is a bit weaker, really, but topologically, you know, if you take a Corbino disk and you stretch it along the axis of a cylinder, then you create these Corbino cones. So the topology of the two things is the same, and maybe that means that their physics is going to be similar. But the sort of killer reason why we feel we can say that this is effectively a Corbino disk is because we have done quite detailed and tricky enough modeling to determine aspects of the current behavior along this cone surface in the presence and absence of a magnetic field. And what we get is that the magnetoresistance expected is directly proportional to the square of the B field applied and the square of the mobility of the carriers involved. Now, I don't really know why I'm showing you this. This is just, to show you we've done some fancy models. But the best model really we've managed to get is it's an iterative summation model that's been used very successfully in established literature for the development of Hall potentials. So what you do is you take the initial current, you pretend there's no magnetic field in action. Then you ask, okay, when you have that initial current, what is effectively going to be the additional current component as a result of the magnetic manifestation of the Lorentz force? And that gives you this J1. Then you say, okay, for that additional current component, what is the additional current associated with it that is associated with the Lorentz force? And that then gives you a J2, and then you do the same to J2, J3, J4, and you end up with a sort of sum to infinity for the overall behavior of the current. Works very well. There are reasons why I would have thought it's not going to work, but works very well and a reasonably established piece of physics. And if you do that sort of sum to infinity, you end up discovering two things. One is that actually there is a Hall voltage. Normally in the Corbino disk, there is no Hall voltage. Here, there is a Hall voltage, but just across the width of the domain wall. Apart from that, it's pretty much the same as the Corbino disk. And all you get is the geometric MR, the same as the Corbino disk, but with this additional correction factor to do with the angle, the conical angle. Okay, so what? Well, we do these experimental measurements. We have the field going down the conical axis of these cones. These are not easy measurements. Each measurement is taken over about 4 days. But what you see when you step the field up linearly is undoubtedly the development of a change in resistance that is parabolic. And you can see directly that parabolic relationship, and you can take log-log plots and see that it is indeed an exponent of 2 that's associated with the MR proportionality to B squared. Okay, fine. Now here's the thing, right? When you do all this, you find out that the magnetoresistance is proportional to B squared, but that the mobility implied is not of the order of hundreds, which was already high, but is actually of the order of thousands in this LNO system. And that is much, much higher than any other oxide system, much higher than graphene, much higher than LAO-STO interfaces at room temperature. So there is some exciting physics here, I think, to be developed further, but the experiments, the measurements themselves are not at all easy. Okay, so time's moving on. So that's my sort of, the progress that we have made so far in trying to access fundamental aspects of transport, carrier properties, and so on. And it's been slow. Okay, what about the other aspect of what you can do with these domain walls? So one of the really exciting things about having a conducting domain wall that isn't really, it's a two-dimensional conducting object, that's exciting. But the real excitement is in the fact that you can have no domain walls, you can have some domain walls, you can create them, you can annihilate them, you can move them from place to place. And so you have dynamic deployment possibilities of 2D conducting sheets. And that dynamic behavior, possibilities of behavior, has been very attractive to us all, I think. And a number of people have shown how you might make devices using the now you see it, now you don't aspect of domain walls. So here's a nice one from the guys in New South Wales, where you can see that, if you have a conducting domain wall straddling source and drain, then conducting AFM shows where the electrode is. If you don't have a conducting domain wall between source and drain, then you can do conducting AFM here on this electrode, but you don't get any currents coming through. Very serious work being done in Fudan by Anquan Zhang and co-workers. And they're probably the ones that are really pioneering prototype devices in lithium niobate domain walls the best. I can't ignore Dennis's work. He's done some fantastic stuff here, again on the manganites, but showing how you might use, ironically, how you might use the contact resistance between the metallic probe and the conducting domain wall and the barrier associated with that contact to create domain wall rectifiers. All good stuff. Okay, what have we done? How much have I got? Maybe 10, 15. Okay, so we've done 3 things, all based on memristive behavior. And I'm going to give you a quick summary of the sort of basics of these 3 studies. The first one I'm going to talk about, we did predominantly at Queen's. The other 2 were mostly done by Alexei Grooverman and his team in Nebraska, to be honest. Okay, so first study first. This is dead easy. So we have a lithium niobate single crystal thin film. We have a top electrode, a lower electrode. When you have no domain walls straddling the interelectrode gap, you get no conduction. As soon as you start to cause partial switching, in other words, you start going around this polarization loop, you change the microstructure. And I don't know how the contrast is here, but you start to develop reverse domains. And obviously then you get these circular domain walls that sort of delineate the boundary between these 2 polar orientations. As you go through the polarization loop, you get coarser reverse domains until you induce pretty much a single domain at the fully poled reverse state locally. Somewhere in between, okay, you start off with single domain, you end up with single domain. Somewhere in between, you get lots of domain walls. And so you expect the conductivity of this device to go up around about the coercive field where the domain wall density is highest. Okay, and that's what you see. So here's a PE loop for LNO. And when you're around the coercive field, you've injected lots of domain walls, conducting domain walls, and that gives you the capacity to carry a lot of current between source and drain. Fully poled state, not so much. Fully poled state on the other side, again, not so much. Okay, so if you can control the microstructure then by injecting different densities of domain walls that straddle the interelectrode gap, you can create different conduction states. And that's all that we're doing here. So we've changed the microstructure progressively by hitting it with higher and higher voltages. And at each sort of increase in voltage, you generate more reverse domains or larger domain wall densities. And so you get a different resultant conducting state. And you can do this at relatively fine levels of control and really get quite large numbers of states associated with these rather simple memristors. Okay, that was the simple-minded thing that we did in Belfast. In Nebraska, Alexei was much more subtle. And what he did was this. He noticed that when you look at the cross-section of the domains within the interelectrode gap of this single crystal LNO, that after some time, the top region of the domain wall starts to lose its inclination angle with respect to the polarization axis. So in other words, this no longer has a polar discontinuity. And therefore, if the conduction is due to the magnitude of the polar discontinuity across the wall, you expect this to go from something that was inclined and conducting nicely to something that is now not conducting at all. And equally, if you find a way to restore that angle of inclination of the domain wall up to the top surface, you can waken up the conduction state. Okay. And that, I think the guys in Nebraska have shown rather beautifully. So you take an initial conducting domain wall between source and drain. These are the currents measured. You apply -1 volt. This kind of shuts it down. It straightens up the domain wall close to the surface. And you see you get a shutdown of conduction. But then you can gradually reawaken that conduction by applying progressively larger positive voltages, and then shut it down again, and do the same old trick. And here you can see, all right, here's the -1. If you hit it with a longer pulse at -1 volt, you shut down the conduction. And then you can reawaken the conduction by either applying larger voltage pulses or by applying pulses for longer times. Okay, so we have these two mechanisms. One is you can change the conductivity by injecting higher densities of conducting domain walls. That's a simple-minded approach. The more subtle approach then that Alexei noticed was you can just change the angle of the domain walls near the surface of the system, and thereby change a percolative pathway into a non-percolative pathway for the transport of current. This last study combines both, and I'm not going to spend too much time on this. We have a graphene electrode, which is nice because you can image through it. But basically, you see that as you go through different applied voltages, you change the microstructure as we had before. And that's one thing that is playing a role here. But equally, also the angle is playing a role. So here's a top surface scan of a domain wall after waking the system up. So it's now conducting quite nicely after 10 volts being applied. And then you shut it down and the wall contracts back in because it becomes vertical near the top surface and the current disappears. So a nice illustration in the same system of the fact that both of these mechanisms for creating different memristive states are acting at the same time. All right, last section then. I would think this is a disaster because we've got when you've got a memristor, surely what you want is you apply a voltage, you get a conduction state, there it is. You want a different conduction state, you apply a different voltage. But when these two mechanisms for creating conductive pathways are acting in parallel, there is great room for complexity in how you actually produce a conducting state. I would say a disaster, but if you're in the neuromorphic community, you might say, oh, that sounds great, because neurons and the synapses between neurons are pretty messy things. Okay, so I don't know much about this, but I'm going to tell you what we've done. So this is probably one of the classic studies of how synapses behave. And synapses are just this little connection between two neurons. So if the synapse resistance is very low, then these neurons speak to each other very strongly. If the synaptic resistance is high, then those neurons are not strongly connected. And so developing strongly connected and weakly connected neurons is a way to develop biological processing. So these guys, Zhang et al., did one of the classic experiments, not very tasteful experiments perhaps, on a fish embryo. And I think they were dealing with the retina here. And what they did basically was they put one electrode onto one neuron, other electrodes onto other neurons, and then they stimulated the synaptic gap with a variety of voltage pulses, and then asked the questions, okay, what happens to the strength of the synaptic connection when you've done different pulsing things to it? And this, I think, is a very telling paragraph from that Nature paper. And what I just want to do is do a show and tell to say, the crucial things that Zhang et al. Have picked up for real synapses are things that we're picking up for our for our domain wall memristor device in the lithium niobate. So first thing, I can't read this because the chat box is in the way. But this first highlighted piece of text is just saying, if you repeatedly hit the potential difference across the synapse, you can progressively develop either its potentiation or its depression. So you can increase or decrease its resistance by repeated voltage stimulation. This is called plasticity, and is something that's very commonly seen in memristive type devices. And we see it in our LNO domain wall devices. Okay, nice. Not only is plasticity important, but then, and I really can't see the word here, but I think it's long-term. It creates long-term potentiation or suppression. Now, if we look at an initial state, so this is a state of conduction that has been set in our LNO domain wall memristors, then if you monitor the resistance of the device as a function of time, it decays away. And so, you know, dreams of long-term resistance states being set in stone were fading away with it. And that fading of the resistance state occurs over milliseconds. It also occurs over minutes. But if you kind of wait for a very long time, you nevertheless see that if you set the initial state with larger voltages or with more pulses, then there is indeed a long-term difference in the potentiation that one gets between source and drain. So the state, although it decays away, after a long time, it is actually set into a particular resolvable state. So long-term potentiation or not. Okay, more things. All right, so this, depending on the time difference between the voltage pulse that's applied to the two neurons, you can either build up the connection strength or reduce the connection strength across the synapse. This is called spike timing dependent plasticity. And this is typical of what you see for this phenomenon. So if you've got two voltage spikes that occur at exactly the same time, then you know, it doesn't like it very much. But if you get voltage spikes that have a very small time difference, then the system adapts to either reduce the conductivity or increase the conductivity, depending on which is the pre and post synaptic voltage pulse. And the idea here is that if the pre-pulse comes just before a post-pulse, then that suggests that these two pulses are connected, cause and effect, and that therefore sets the synapse to recognize this somehow by reducing the resistance of the synapse. I don't know much about it, but it's classical for the development of synaptic response. Can we see it? Yeah, we can. We have to be a bit careful about how we set up our initial state, but we can see this form of spike timing dependent plasticity and the reverse form depending on the initial state that we set the system into. And then the last thing, which I'm quite excited about, is also another classic thing that people look for in devices that replicate biological behavior. And this is the Ebbinghaus forgetting curve. So what Ebbinghaus did was he had a whole list of syllables that were just nonsense. He tried to memorize a list of syllables and then recall them after certain amounts of time. And then he found that if he were to re-look at the list and try and memorize it again, then he forgot more slowly. So his recall was much better. And after the third review, his recall was significantly much better than it had been had he just looked at it once. So, I mean, this is not rocket science. This is revision for exams. Okay, so this is called the Ebbinghaus forgetting curve. Our memristors show similar behavior. So here is the first decay off in the memristive state as a function of time after we've set it initially. If we reset it, remind it what its set state was meant to be, then you can see that the fall off in the conduction level is much slower than it had been after learning only once, after setting it only once. If you remind it again with a second reminder, second revision, then the fall off in the memory of the state is even less severe. So we think this is quite interesting because not only is this representing, it's a memristor representing a single synapse, but it's now representing function of an entire brain. Okay, forgive me, I've used a lot of time. The summary is, all of the fundamental experiments we've done suggest very high carrier mobilities, unusually high carrier mobilities in domain walls, suggestive of quite exotic physics. And the rest of the stuff we've done is just to show that you can make very effective domain wall memristive devices using lithium niobate domain walls, which are starting to show some real promise in terms of duplicating aspects of synapse behavior in biological systems. And I'm going to leave it there. Thank you. And I hope we didn't steal too much time.
Thank you. Thank you for this very nice talk. Now, questions?
So about those very, very high mobilities, can you speculate about this amazing physics that may be behind?
Can I speculate? I don't know. Is that Jorge?
Yes.
Hi, Jorge. So I mean, I'm hyping it up a little bit, you know. So on the one hand, you know, these are amazing figures, order of magnitude larger than you would expect or have ever seen in any other oxide. So that does make it remarkable. On the other hand, the absolute mobilities are comparable to what you would get in like an intrinsic semiconductor, you know, like the purest single crystal silicon. So, you know, that makes it sound very unexciting. But I do think there's something interesting going. So I guess what I'm saying is that, you know, getting a 1,000 or 10,000 square centimeters per volt second isn't unheard of. You'll get those kinds of numbers in beautiful single crystal intrinsic semiconductors. So it's not unphysical. It's just that something's going on that is making the oxide sheet behave a little bit more like a high purity single crystal intrinsic semiconductor. What that is, I don't know. So I'm avoiding your question, but I'm trying to say that it's unusual, but it's not kind of ridiculous.
Right, but it's very, very unusual, right? Because this domain wall, in principle, is very different from silicon.
Absolutely.
Crystalline silicon or anything
Absolutely.
like that. I mean,
Yeah. And you know, I guess when you compare it to other 2D systems, and I think that's where we got most excited, is, you know, if you do a cursory look for things like, you know, chiral mobility and graphene and LAOS here, you get absolutely huge numbers, you know, 80,000 and so on and so forth. But those are cryogenic temperatures, not at room temperature. And at room temperature, the mobilities are pretty modest. So I can't speculate, Jorge. I don't know what the physics is. I'm not gonna pretend. I'm going to explore and see if we can find out more.
Just a quick follow-up, Marty. So I think there has been already some DFT studies of those domain walls, or domain walls in lithium niobate and partly charged, or let's say not straight domain walls. Have you looked at those? Did they see anything in the electronic band structure or the atomic structure itself that, you know, coming back to them? I mean, probably nobody thought about something like this, probably, right? But coming back, is it worth it? Because I think there is some literature on that.
I haven't seen literature on it, but you know, I'm not in command of all the literature, Jorge, so it may well be out there. I haven't seen it. Anything that I've seen shows, you know, very sort of flat bands with, you know, relatively steady band gap, very unexciting. You know, the fluctuation in the states in the conduction band and in the valence band are very minor. So you get these very flat bands. What we were looking for actually was a very deep, sharp band with a lot of curvature. So getting back to things that Pep was talking about and so on. So we imagined that if you had a very high curvature conduction band induced by some, you know, different electronic structure because of the difference in physical structure at the wall, that might be a good reason for very, you know, low effective mass carriers giving you ridiculous mobilities. We tried to do ARPES measurements, but the ARPES gave us no, I mean, we saw signal, but the signal that we got where we'd written domain walls was indistinguishable from the signal that we got where there were no domain walls. So, you know, either we weren't actually probing the walls because they collapsed to become vertical again or something, or there's another mystery there that still needs to be solved. I was hoping for very, you know, one of these, like, I was hoping for Dirac cones is what I'm really hoping for.
Hi, Marty. This is Marin.
Hey, Marin.
Very nice talks. Let me point something so we can discuss later on this. Is that at the end of the day, you measure through this domain wall a current which is, in my opinion, ridiculously low. So you have a few picoamps. So if you make the comparison with a tungsten diselenide or molybdenum disulfide, which is 1 atom thick, with a relatively low compared to your mobility, the current is a 6 order of magnitude higher. So I think we are missing something like 8 orders of magnitude in terms of current density.
Yeah, so
that's something we have to think about.
Yeah, I mean, I'd make 2 comments. The first is that when you look at, through the Hall measurements, you can also extract the carrier density, and the carrier density is extremely low. I mean, really extremely low. And that's something, again, that the first time we saw it, we didn't really believe it. We thought, okay, it's a nice technique, but the numbers are probably wrong. But we've done it many times, and always we end up with a carrier density that is many orders of magnitude lower than the density required to screen the polar discontinuity. That's the first thing. So it could well be that you have very high mobilities, but extremely low carrier densities. But the other thing is that we need to look carefully at the data, because if you drive these things pretty hard, you can get microamps. So the 8 orders of magnitude sort of gut feeling might not actually be there. We need to look at it, Maren, but we'll do that because we're going to be working together on it anyway.
Hi, Martin. Nice talk. This is Uwe. In hafnium oxide, if we look in the FIFET structures, we see also this spike time dependent plasticity. We can have either different voltages applied or different pulse lengths applied, and we get this memoristic behavior. And I was wondering, I mean, is there maybe a correlation between the switching you do and the effect you see on the domain walls? I mean, since you have also, you're applying the voltage to the whole film, and maybe you have also gradual switching of your ferroelectric properties in the device, and this impacts then the domain wall related to it.
Yeah, I think that's true. I think there are 2 things going on in parallel, both of which are dictated by kinetics. So one is the degree to which the system is becoming switched, as you suggest, and the other then is this rather subtle thing to do with the domain wall angle with respect to the polarization. We're not the first to see that, I should stress that, but it's these 2 things going on at the same time that I think leads to an awful lot of the complexity for us. But in your case, is there any evidence of domain wall tilting in hafnia? I don't know.
So in hafnia, the problem is that, we have quite small grains. They're typically like 20, 30 nanometer, and we even have domains within grains. So with PFM, nobody was able to resolve domains within hafnium oxide. So due to the very small structures, and so yeah, it's probably tough to say if there's any evidence of this.
Okay, but that would be exciting, right? That would be exciting.
The thing is probably if there would be somebody able to make larger domains. I think now you can see, there's some work on bulk hafnium oxide which showed at least 100 nanometer domains, and maybe with progress in epitaxial, or I don't know, Mal was looking at me, he was telling me this 10 years ago, yeah. That's possible maybe to do, yeah. Yeah, I'm sorry.
So sorry that I interrupted this discussion. Maybe we can talk by emails or messages. We have another presentation. So Marty, thank you again for your presentation and for staying with us. Yes, I know. It was Alexei Gruberman scheduled for the last presentation, but he announced me that for some reasons he cannot be with us in this evening. So we decided to move one presentation from Thursday just before lunch to have more time for lunch and for leaving to the airport. Yeah? So I invite my young colleague to visit the city. Oh, only from the taxi. You can see the city in this evening. The institute tomorrow. Yeah. So my colleague is Marius Hușanu, and he will talk about ferroelectricity and rhomboidal distortion in the electronic band structure of strained PZT. So you have around 25 minutes max with question and answers.
Thank you. Thank you. I'm glad that I have the opportunity to present you some of my recent research, which actually are work under progress, and to hopefully entertain you just before the dinner. And I will focus on the electronic structure of ferroelectric lead zircon titanate PZT in angle resolved photoemission in ARPES. I will shortly introduce you the ARPES technique and then go to the electronic structure of PZT obtained in our measurements, and end up with some conclusion and outlook. When we are thinking of the functionality of materials, at optical properties, whatever properties, it's just easier not to look at directly the amorphous material, but to put the atoms into periodic potential, and there we know that we can define some wave functions. We know that the atoms, as we bring them together, define energy bands, which we can solve analytically or numerically and obtain the energy of those bands. We have wave vectors, we have a periodic potential, so depending on how the energy of these bands vary on the reciprocal space, we have either electrons which disperse like that, we have holes which disperse like that, light and heavy, and basically they encode all properties, electronic properties, and the functionality of materials. How do we exactly measure this in ARPES, in angle resolved photoemission? The technique is a particular case of photoemission, which is an photon in, electron out technique. We hit the sample with a flux of photons. We record the energy of the outgoing electrons. If we vary the angle of the sample with respect to the measurement plan, we can establish a one-to-one correspondence between the energy, the kinetic energy of the electrons, the angle, relative angle of the sample, and binding energy wave vector. And from this technique, we extract information on the composition of materials. And if we look into the valence band, we can draw conclusions about how the orbitals overlap, what is the effective mass of the quasi-particles, what exactly do we have there, electrons or holes. And for example, we can directly decide if a material is populated by holes or by electrons, or for example in oxides with coexisting electrons, electron band and hole bands, we can directly isolate them. Depending on how well the wave function overlap, we can have larger or smaller bandwidth, which actually define the effective mass of the electrons. A better overlapping wave function define an electron with smaller effective mass, larger mobility. We can look at the bands which do not disperse. If their wave function do not overlap we will see in angle resolved photo emission just undispersive levels. These are impurity levels. They can be thought as levels with infinite effective mass because they do not overlap. And why focusing on the band structure of ferroelectrics? We need to admit that ferroelectrics are underrepresented in RPS measurements. And I have two clues why this may be. One of them maybe is not that interesting to look at insulating states with completely filled orbitals located at -2, -3 eV. Or maybe it was just not possible to look at them due to charging effects and due to the fact that in normal VUV RPS measurements, you probe only half nanometer at the top of the surface, which lies exactly in the band bending potential of a ferroelectric. Basically, you will have some smeared features not being able to see anything. I'm summarizing here what do we expect to see in a ferroelectric with a well-defined orientation of the ferroelectric polarization pointing either away from the sample or towards the sample. We will have a bending of the band structure towards lower energies and higher energies, depending on this direction of the ferroelectric polarization. Imagine that we have a freestanding ferroelectric layer which is not compensated, which doesn't have its well-defined ferroelectric state compensated by metallic electrodes. Then we will need to have compensating charge sheets located close to the surfaces, both surfaces of the material. And depending on this direction of the ferroelectric state, we expect to see near the surface the signature of either electrons or holes compensating the ferroelectric state. That was the idea, the initial idea of the experiment. For the perspective, if we are interested in enhancing the functionality of the ferroelectric by doping, we are much interested to see what is the signature of the impurity bands. And in angle resolved photo emission, we could, in principle, see this. What was the system we choose to look at was a thin ferroelectric PZT, 5 nanometers. At this thickness, on the one hand, we know that it does not develop domains. So when we probe in photo emission, we are sure that we are not mixing up the signal from the domains pointing upwards or downwards. On the other hand, we know that this freestanding ferroelectric at this small thickness needs a lot of intrinsic charges in order to compensate the well-defined ferroelectric polarization, and this almost 1 order of magnitude larger density of intrinsic charges compensating the well-defined ferroelectric state prevents from charging effects, which otherwise precludes the detailed band mapping of PZT. First, we look at the electronic structure of. So maybe I think I forgot to mention from XRD measurements we noticed that our PZT is in highly tetragonal, highly strained state with a C/A ratio exceeding that of the bulk one. So in bulk is 1.04, our value is 1.008. As we increase the thickness of the PZT layer, the tetragonality ratio decreases towards that of the bulk one. This is the electronic structure computed by DFT, and we clearly see that the valence band is a coexistence of lead and oxygen states, and the conduction band by empty titanium and oxygen orbitals. This is the Fermi surface at the valence band maximum, and we see that we expect hole pockets in the X points of the Brillouin zone. And as we go deeper into the valence band, these hole pockets increases, and some states will appear here in the Z point. By doing synchrotron radiation RPS measurements while varying the energy of the incoming energy, we probed the electronic structure of PZT along this direction, and the isoenergetic cuts which we obtained are here when the value is that corresponding to the valence band maximum, which is this one, right? If we choose a value of the isoenergetic cut energy more deeper into the valence band, we see that in the Z points appear the predicted features which we have here. And we know for sure that this isoenergetic cuts corresponds to the PZT in ferroelectric state, because in a paraelectric state, this is how the isoenergetic cuts should have shown, with this pocket in the gamma point, not in the Z point. Okay. Also, we know that it is in a ferroelectric state by comparing our X-ray absorption measurements with those previously found in the literature, so we have an excellent agreement with previous data. Now we look at the isoenergetic cuts performed into ZRA plane, and if you have in mind that hole pocket which should have appeared here, we see that at the valence band maximum we have it, but in addition we have also some 4 additional features which do not correspond to the tetragonal phase of PZT. The same additional features are seen also when the isoenergetic cuts are performed at energy more deeper into the valence band. Our explanation is that of a rhombohedral distortion of the PZT, which is quite uncommon for this doping level. PZT 02 is known for its tetragonal state, especially when epitaxially grown on STO. To better see the association which we did, to explain the additional features as being due to rhombohedral distortion, we see that the feature basically originates in a folding of the fundamental band structure into Brillouin zone corresponding to low symmetry 1. Basically, the features appearing in the A point corresponds to cutting the rhombohedral Fermi surface calculated here along the central plane, which is gamma 1 crossing through gamma L line. Similar phase transition to lower symmetry 1 were previously seen in other oxides as well. For example, in lanthanum strontium manganese oxide, we see a folding of the band structure so that when cutting through the gamma point, we also see features of the which are associated to the corners of the Brillouin zone. When cutting through the topmost region of the Brillouin zone, we see projections of the gamma point there, which correspond to the fundamental tetragonal lattice. Signature of orthorhombic distortion in other manganite, cerium doped calcium manganese oxide shows the appearance of additional features to the fundamental cubic lattice corresponding to the orthorhombic lattice here, in addition to the fundamental lattice. And this is how the band structure of PZT looks like along the gamma X direction and RAR direction. We see that the spots in the corner of the margins of the Brillouin zone cannot be explained only by the fundamental tetragonal band structure, and we need to assume that there is some folding of the band structure, so that in the A point we have the band structure corresponding to the gamma point in the fundamental tetragonal lattice. Okay, what is interesting is that rhombohedral distortion is seen up to the room temperature. The presence of these additional features in the isoenergetic cuts and in the band structure, which is quite uncommon because okay, it has been seen that while lowering the temperature, the crystalline structure goes to a low symmetry one, and the measurements have been performed at 12 K, but at room temperature to have this rhombohedral distortion, that's quite uncommon. And it seems like this phase transition towards the rhombohedral phase is substrate induced. PZT was grown on LSMO, lanthanum strontium manganese oxide, which is known to feature a rhombohedral distortion. And recently has been proposed some mechanism of propagation of octahedral tilt and rotation from the substrate to the towards the top layer up to a thickness of 2-3 nanometers. So we believe that that's the explanation of this rhombohedral phase. Basically, our PZT mimics the crystalline structure of the LSMO substrate. And now we have in plan to do measurements on STO, which is cubic, and we expect to see the absence of this reconstruction. In our perspective is to further look at these ferroelectric materials doped with magnetic impurities, and in this context these measurements will be the reference, and we have in mind to look at the impurity levels, which should be located somewhere between the valence band and the Fermi level, and then to infer functionality, the possibility to inject charges depending on the energy between the Fermi level and this impurity band. Moreover, the relevance of this rhombohedral distortion probably have some impacts on the functionality. A PZT grown in a tetragonal lattice means that the off-centering of the central atoms in order to define a well-defined ferroelectric state can occur only along the z-axis. On the other hand, on the rhombohedral phase, it will probably, at this level is just speculation, probably will occur easily, but that we'll see. Thank you.
Okay. So, if you have questions.
Which is the advantage of using ARPES to identify the impurity levels in this compound rather than photoluminescence or standard optical measurements? Why you use ARPES to get information of the impurity levels?
Having information on the impurity level by itself maybe is not important, but if the impurity level is close enough to the valence band, it will give you also information about band hybridization between the impurity band, which cannot be derived in other measurements.
No, that's true, but do you have already information of the impurity levels by a standard optical means on these samples? So do you know already that you have impurities, and which kind of impurities do you have before going to ARPES?
Well, this is the standard sample without any impurity. So that is just the bare sample, right?
Okay. It's a bit complicated. Okay.
Yeah, thanks for the talk. I was a little bit confused about the terminology hole pocket, because you said that there's a hole pocket at the top of the valence band. Now, usually pockets, it's when the band crosses the Fermi level, and you either have an electron or a hole pocket because the band is crossing. But by definition, at the top of the valence band, there is no crossing. So
that was, of course, a mistake. It's just the top of the is the valence band maximum.
Oh, okay.
Obviously, at the Fermi level, there's no crossing. So PZT is in the insulating state.
Yeah. Okay. Another question: have you seen any effect of charge transfer as a function of polarization from the LSMO electrode into the PZT, which could, for example, dope one way or the other the PZT and therefore shift the bands?
Actually, we had in mind to look at. We realized that the thickness of the PZT is too large to see anything from LSMO. So basically, we don't see the bottom interface. We see just the surface probe. Let's say maybe in the range of 2-3 nanometers. Out of these 5 nanometers, the entire thickness. And just to continue about the motivation, our motivation was to identify the energy of the electronic states which compensate the ferroelectric state. Looking here in the band structure, not seeing any impurity level, any electron on hole related state, what we may infer, the only thing is that if they exist, they are above the Fermi level, and in photoemission we see only the occupied level, or they are incoherent. They don't have a well-defined energy. Okay.
So how much of the interpretation of your ARPES data relies on the first principles calculation of the electronic structure? For example, when you said that you need some kind of zone folding to understand what's going on the A point, that's because you are comparing against first principles data, or is all or comparing with different experiments that
historically, we try to interpret our data only with the band structure of the tetragonal cell. And we see that in assuming a perfectly tetragonal unit cell, we would expect only this point and not these additional features.
So that's from symmetry analysis alone, or from first principles data?
For first principles.
From first principles.
Mm-hmm.
So okay, so the folding, for example, comes from the fact that the model you use for the first principles calculation doesn't contain that, right?
Doesn't contain.
So essentially,
afterwards we calculated we did our first principal calculations in the rhombohedral, rhombohedral
Yes.
cell,
So
which
about
is
that,
this one.
So your rhombohedral cell that your field inherits from the substrate, that this includes tilts, presumably, of the octahedra and all that, right? So isn't there any evidence before your ARPES data of whether that happens in PCT grown on LSMO? Because this must be a field that has been looked at by X-rays, whatever, and this kind of doubling of the unit cell, for example, this in principle should show up, I would imagine, in some experiment.
And I would have expected to see, at least in XRD as well, but to my knowledge, there is no such data.
I mean, it's funny that you discover something like this by doing ARPES, of all things, right? Because, you know, it's a... Oh, no, right?
Okay, you can discuss later. Thank you, Marius. Now, we are leaving for dinner now. Tomorrow, because Brahim could not come, we start later. So you will meet at the hotel with the bus at 8:40. 8:45 latest. Yeah? And we will start at 9:40 here. Yeah? So now we can, I think the bus is already here, so